All right, so hello everyone to the second session of this 2020-2021 Palaisien Seminar. We are very pleased to welcome you. We are a growing community. We are 54 right now, and there is like 70 people registered for the Palaisien today. So it's good. Don't hesitate to spread the news. And as we are in a remote conference system, don't hesitate to spread it even outside of Université Paris-Saclay if some people are interested in the talks. So today it's a great pleasure to have Alexandre Gramfort, who will talk about learning representations from neural signals. So Alexandre, the stage is yours.
Okay, thank you, Thomas, Victor Emmanuel, and the organizers for inviting me, and for the attendees to be virtually present this afternoon for this lecture that aims a bit to cover various types of works around representation learning and deep learning applied to neural signals. So let me first start by maybe try to give a bit of background by what do I mean by representations. In the case of a historical case, or in a common case of working with audio, when you study representation in a textbook, people will often talk to you about the short-time Fourier transform, which looks like this. It shows you what other people call you the spectrogram. Fourier transform that you applied on frames, successive chunks of data. And it allows you to look at the data and make sense of it. Another example that you see here is the orthogonal wavelet of a famous picture that some of you who studied the computer vision or image processing many years ago have surely used many times. And it also allows you to decompose, and it can be used, for example, for denoising. And but beyond these famous applications, you can find representation across different disciplines. What you see here is in the context of diffusion MRI, where people have used spherical harmonics to represent or decompose signals, which is here defined over spheres, that allows you, for example, to find fiber crossing in the brain, or fiber orientation, basically the pathways or the highways in the brain. So these representations, in a sense, are useful to look at your data and basically provide something that makes sense for the human eye, allows you to denoise data. It also allows you to build some predictive models in a supervised learning context. So kind of the aim of this talk is to look at this representation when we talk about brain signals and neural signals. So let me first introduce what I mean by brain signals for some of you who are not familiar with these types of signals, which I assume is a lot of the audience here. Here, if you have a piece of cortex that you see here in yellow, that is the gray matter. This gray matter will produce, when you have active neurons that you see with these red arrows, these active neurons will produce electromagnetic fields that you can measure outside of the head, basically non-invasively, through measurements of the electric field, through the electric potentials, or the magnetic field. So these are ways to basically measure neural signals in a non-invasive way using techniques that are called electroencephalography, or EEG, or magnetoencephalography, also referred to as MEG or MEG. And just for historical perspective, we've been recording EEG for almost a century now, and the types of MEG system we have access to these days are roughly 30 years old. So you can also measure brain signal invasively, typically on human patients or also animals that are implanted, by basically just sticking electrodes inside the brain and measure the local potential, electric potential in a specific brain region using a fine resolution. So in the end, you obtain many signals. For example, that you see here is an actual recording of an electric potential, where you see a slip spindle, which is the high-frequency burst that you see right here, but also a K-complex that we'll also mention later. But you can find also and that basically suggests that you have these waveform shapes that are prototypical of brain rhythms. And you also you have these types of funny phenomenon where here you have some kind of slow wave, and on these slow waves you have these high-frequency bursts that appear, and basically people have described this as a way to have different neural populations to communicate. So these are really uncommon patterns for when you're only familiar with computer vision or NLP or other types of AI data, but they are also really relevant for neuroscience. So the outline of this talk is basically 3 routes to representation learning using EEG and MEG. And we'll start by the supervised, and we'll see then the unsupervised way, and we'll conclude with the semi-supervised way. So I cannot see you laughing or smiling, but I hope that this joke made you smile. All right, so the first part of this talk is really on, I would say, standard deep learning, supervised learning when applied to EEG data, and typically during sleep, and we'll see in a minute why. So when you basically have sleep disorders, which is unfortunately very common in our modern world, you have to go through what people call a polysomnography or PSG. So the people in Paris may refer as PSG as something different, but here it's the context of polysomnography. And basically you will measure potentials over the chin, over the eyes, or over the brain through EEG. And you have all these multimodal signals that are recorded over the entire night to kind of diagnose if you have some sleep disorder. And the interesting aspect about this data, since it's a clinical exam, you have many experts that are paid the entire day to annotate this data, which is a good opportunity for machine learning to work with well-labeled annotated data. And the first thing that people try to do with these types of data is build what people call hypnograms, or basically the sleep cycles that you see here represented in this plot, where you have basically the wake sleep. This is the rapid eye movement of people also called sommeil paradoxal, when you dream. And then basically you go into deep sleep to go into N3, which is the deepest level of sleep. This is the first, basically what people call the macro structure of sleep signals. And what you see at the bottom is another case, which is here the sleep spindle that you see represented here, where people call micro events. So at the end of the day, the first case is really a classification problem where every chunk of data needs to be associated with one of these 5 stages, whereas the other problem is very close to basically an object detection problem when you need to detect of events. Is it a spindle or a K-complex or something different? So if I frame this now in a machine learning jargon, basically I've got my polysomnography data, this multivariate time series. I will have an observation, which is really 30 seconds of multivariate signals. And what I'm aiming to do is basically learn a function, f, so f hat, that will go from the space of multivariate signals, but potentially multimodal, and we output one of these 5 stages, so awake, rapid eye movement, or different sleep stages. So it's really a multi-class prediction problem where the input is a time series. So if you step back and you look what's happening in this literature over the last few years, there's been a kind of a growing interest in using deep learning on EEG data. And what you see here in orange is related to papers that are applying deep learning on sleep. And you see that it's really a very active field right now. It's also be used for other clinical contexts like epilepsy or cognitive tasks. But here the topic is really sleep. So the way we approach this problem is the following. We're going to work with naturally a convolutional neural network because we have some insights from the data that we have some spectral content that is basically prototypical of certain sleep stages. And also, we know a few things about what works on these types of data. So we have multivariate signals. So what is very common is to do linear combinations of input signals in order to denoise. So what people call spatial filtering, or for deep learning people is basically 1D convolution. And then each modality, so EEG, EOG, or EMG, they have different spectral content. Basically, your brain does not produce the same types of brain rhythm for the same receptive fields for the filters, or the EMG tends to produce also higher frequencies. So all these modalities have subtlety in terms of the spectral content, and we will use this in an architecture. And really the last part is really exploit the fact that when you look at these spectrograms, you have a sequence of states. And we'll see kind of a simple idea of how to address this issue. So we have a machine learning problem, supervised. We want to minimize the empirical risk with respect to our distribution of data, which is a joint distribution of X and Y. And L is our training loss. And so the function class we'll be using is basically a CNN with what I will describe in a minute. And then the loss is just simply a cross entropy, as we have a 5-class classification problem. So nothing, I would say, uncommon at this stage. So in these types of data, we have this spatial filtering, so the linear combination of the data, and then we basically have 2 layers of really standard off-the-shelf blocks, which is convolution, rectified linear units, and then some max pooling to reduce the receptive, basically increase the receptive field with depth in order to cover the input signals, which are roughly 30 seconds. Okay, so basically one novelty is that we process these different modalities with slightly different chunks in the neural architecture. And then in order to take into account time, we do something quite natural. We learn this representation, which is really the output of these 5 functions that will be outputted into the softmax layer. This output representation that we learn in a supervised way will be pulled from different windows, the previous one and the following ones. We roughly consider that in the context of sleep, you need 1 minute of data before and 1 minute of data after to get an informed decision about the stage of the window that you're looking at. And this is really the way we approach this problem. So really to conclude on this first part, we did some experiments. And so we use an entirely public data set. So it's the mass data set, which is a data set from Canada, which is roughly 61 nights, and which is about 60,000 samples. Just to give you an idea for the deep learning people in the audience, it's as many samples as you have in NIST. So for, I would say, biomedical applications, it's a lot of annotated samples. It's really huge compared to what we're commonly using in medical applications. We use different cross-validation procedures, nothing fancy, and we'll be comparing with what people have done in the past, which is really to use handcrafted features and tree-based methods like gradient boosting or random forest. And we'll compare with different architectures. So really going quickly over this first set of results, what we see is basically 2 aspects. Is when we pool the multivariate nature, when we use all the modalities, not just EEG, we get a big boost. And also when we take into account the temporal information, we also get an improved performance. And one of the claims of this paper is also that the architecture that we propose is in the sense a bit frugal, in the sense that we have less parameters and we have a faster running time than the competition. All right, so this is really I would say, deep learning 101 on EEG, and a more involved application will come in a minute. But before, what we basically want to learn in terms of application is, okay, what is the representation capturing? So what we can look at is basically really what is the confusion matrix, how the stage, that the N1 stage is very often mixed with the rapid eye movements. But otherwise, the deep sleep is well recognized. And then we can also do some kind of ablation study, which is also classical, I would say, more in images, where you kind of hide some part of the image in order to figure out what the network is using. And here what we do is basically we hide certain frequencies. And for example, what you see here is that you've only conserve or keep the frequencies around 10 hertz, which is this alpha wave, which are prototypical of attention and being awake. You see that the network will consistently predict that you're awake. So in a sense, there's no big surprise, but it really shows you that the network has learned by this supervision what we knew already in terms of neuroscience, and basically how the data were actually labeled by the sleep experts. So now the second application I want to mention in terms of deep learning and representation learning is a bit more involved. It really involves into the detection of these micro events. So this is a paper that now was published 2 years ago, and it really was the first paper that aimed to apply these types of detection architecture to detect these micro events in EEG during sleep. So we want to predict basically what and when events these micro events occur. So the types of data that we have access to is these spindles or K-complex. And really what the network should output is given continuous recordings to say, where is there an event, when does it start and when does it stop, and And then if there's an event, what is the type? Is it a spindle or a K-complex or something else? And why do we care about these types of micro events? Is basically these prototypical patterns are involved in certain sleep disorders. People will tend to basically count the number of spindles that you see in the recording as a biomarker of certain sleep disorders, or basically count if they could observe some K-complex, how often do they occur, and these types of things in order to figure out what you're suffering from. So people have done this problem. It's a very old problem, but so far it was not addressed with deep learning. And so it's really the contribution of this work is try to see what we can do with deep learning. And you can imagine all types of signal processing techniques that have been proposed in the past. Filtering, thresholding, clustering, many things. So the dose algorithm that we propose basically will try to predict the start and end time of every event. Will deal with multiple events. And the aim is that it only does one pass over the data to detect and classify. And for those of you when we did this work, the state of the art, or at least something architecture that was big success in computer vision, were YOLO or SSD that heavily inspired this work. So the way we basically evaluate the matrix is we look at what people call the intersection over union. We want to basically detect that if you have a good overlap between the predictive events and the true events, you have a true positive, and the overlap is little, then it's a false negative. And then we're gonna, once we have the events, for each of the events, we need to predict which class it corresponds to, which gives us a prediction, measures of precision, recall, and F1. So in terms of results, what you see compared to other, I would say, non-deep learning approaches, that you can get a huge boost by using these types of deep learning techniques across 3 different data sets. So every column is a public data set that we've used. And you can see here in blue that deep learning allows us to have, on this problem, a big boost compared to the state of the art. Just an illustration to basically get you a feeling of what it means to look at EEG data when you're a sleep expert. Everything looks like noise for the untrained eyes, but here you have a true sleep spindle that you see here. This is what is true and what is predicted. This is another example, and really this involves, and so the network is predicting a sleep spindle, but the expert is considering that it's not a true one. Is it an issue of the labeling? Is there something else? But this is the reality of the complexity of these signals. Okay, and what we show also is that we can work with 2 types of patterns at the same time, and we also get a boost by combining different patterns. Okay, so now I'm jumping to the second part of this talk, which is really the unsupervised way that maybe Thomas has presented in the past in the Palaisien, but I will insist more on the neural aspects and the applications. So what we're trying to do here is to learn the morphology of brain waves. And what people have done for many years is just to apply linear filters of this data. So here you have this mu wave, that's same as here. If you apply a temporal filter, a linear filter, you make this wave and you make it look like a sinusoid. So the claim is that as soon as you filter data with linear filters, which people do in practice, everything looks like a sinusoid, and people talk about oscillations and completely discarding the complex morphology of the signals. So what people have done to learn representation, basically I would say now for the last 20 years or more, people have also looked at how to learn these representations from data, including using shift invariant representations 15 years ago. And also now more and more in the context of neuroscience, people have came up with strategies to do this, which are more or less heuristics or computationally efficient. So really what we're trying to do here is imagine you have a signal that looks like this, that contains these patterns. This signal can be basically regenerated by convolving an atom that you see here in orange with these spike trains that tells you when is the onset of these atoms. And this is really a convolutive model. where your data is now expressed as a sum of different prototypical atoms. So here we only have one, but you could have k different types of atoms. And here this is the when things happen, and here what is the shape of the atom that is produced. In the end, when we want to estimate, again, both the Z and the D, so this is a kind of a blind deconvolution problem. We want to estimate jointly when the atoms occur and how the atom look like. Boils down to an optimization problem that then you need to solve as fast as possible. That is combined with a sparse penalty that you see here in order to have these sparse spike trains that you see here in green. So there are many ways of solving this problem. One of the contribution of people who have worked with me on these problems was try to come up with the best strategies to solve this. If you look at the problem, either updating D or Z, basically alternative minimization, you have different strategies. And since we need to work with real data that potentially are multiple gigabytes, when we have a solver that is 10 times smaller, we start to have things that are doable that otherwise would not be doable. So optimization details matter. And really the most recent word that we're using is using this locally greedy coordinate descent for the Z update, and then a proximal gradient descent or LBFGS depending on the shape of the atoms for the T updates. The funny thing is that the first order techniques like FISTA or ADMMs are clearly not the state of the art for this problem. This is what we show here is that using either LBFGS, which is a second order approach, leads to big boosts and outperforms other techniques that have been proposed either based on ADMM or FISTA approaches. So this is an example of what you would obtain if you apply this to real data. Okay, so here before, and you see that you recover these high frequency bursts. Basically, you have atoms that reveal these high frequency patterns in the data that are prototypical for these types of recordings. So one of the contributions of the group has been to extend these ideas to multivariate data, which is really critical when we work with EEG or MEG. Because here, when you exploit the multivariate nature of the data, you can go, for example, from here to here using here a technique called ICA. So here, everything looks like the same signal. You see these spikes, but these spikes are actually blinks or artifacts. When you unmix all this, you can decompose the signals. Here it's completely linear, and you can reveal more subtle effects in the data. Like here, this is the heartbeat that is popping up. You have these high frequency oscillations. So in the jargon of ICA, this is the X data, and this is the latent sources that you try to estimate. More formally, when you run ICA, you're basically summing a bunch of rank 1 matrices in order to explain your data X. So you say that X is equal to AS. Both A is unknown and S is unknown. A is called the mixing matrix, and that you're trying to recover. And S is the latent sources that you're also trying to recover. And so when you decompose this matrix product, it's just a sum of rank 1 matrices. And people look at this ICA by looking at one column of A as here what we call the topography. So basically it shows you an activity over the sensors, over the EEG sensors, and here the time course. And this ICA has been used heavily and cited tens of thousands of times in the context of neuroscience because it allows to reveal here very nicely blinks or artifacts or here brain signals. So when we apply the convolutional sparse coding approach to these types of data, we change a bit the paradigm, and we try to decompose X as here a component, which is going to be here a topography, here a time waveform, and really when is the temporal activation are going to occur? Basically, when is this waveform going to appear in a blind deconvolution technique, where here we assume that the latent sources that are unknown is made by basically repeated patterns that are repeated over time. And again, this boils down to an optimization problem, where here you have some data that's called X, and you're trying to approximate this data using a vector of activations, and here this UV transpose that is basically this rank 1 that are coming from here. You might wonder why the rank 1 makes sense. Is because we know from the facts from the physics that the propagation is a linear the underlying model that we use here. I'm not going to go too much into the detail of the optimization of this, but really, again, a big contribution of our work is to come up with efficient solvers to solve this problem on large data sets. And so when you apply this to, for example, a data set with roughly a gigabyte of data, you find things like this. So you have these atoms that are basically mapped inside on top of the sensors that you can map inside the brain, and you can look at the waveform shapes inside this region of the brain and look at and basically explore what's happening in the data. So this is really completely unsupervised. And what is a bit, I would say, striking and exciting about this research is that it allows us to see things that obviously we knew and also new things. So this is an example that I took from the web page where we've put the software to run these types of analysis. And what you see here is the temporal pattern of a temporal, so the spatial pattern of a temporal pattern that you see here. And this temporal pattern is nothing more than a heartbeat. So this is really the QRS component of your heart that is beating. So you see that this MEG device, which is maybe 50 centimeters away from the heart, is able to capture the magnetic effect of the heartbeats. But you also recover the blinks, and you can also recover temporal patterns that are really coming from bilateral region inside the brain, or here an evoked response that is coming from the ventral region in the visual areas, and here also an atom that people will call an alpha oscillation on the parietal region of the brain. So this is really, for me, an exciting new tool for neuroscience in order to look at the data in a different way. So now I want to conclude this talk by the last part, so basically the self-supervised way, which is really the work of a grad student called Hubert Banville, who has basically took a different route to learn representations from EEG using a new paradigm that now people call self-supervision. So what is the idea of self-supervision? Let me start by basically a small detour by computer vision that all of you can understand. This is now a fairly old world in the deep learning standards. It's 4 years old. It's basically a work where they took real pictures and they trained a deep neural network to solve the jigsaw puzzle. So you have this deep learning, you have this natural image, and you take these pieces that you pay attention to keep a bit of distance between the patches, you scramble all this, and you ask the net all the data that is generated completely in a synthesized and automatic way. And so you can basically build an infinite data set using this technique. You only exploit the original structure of the image. And so we will use this to learn representation. So this representation is going to be the output of what people call the feature extractor. And here, basically, we have two terms of the self-supervised jargon that I need to explain. You basically have the supervised pretext task, which is here solving this jigsaw puzzle. So really the task that you don't really care about, you don't really care about solving jigsaw puzzles, but what you care about is having a representation or a feature extractor that is coming of your deep neural network that then can be used on another task, which here called is the downstream task that you really care about. For example, object recognition. So we apply these types of techniques on EEG. So we have different strategies, but for the sake of time, I will explain just the simplest one. And the idea is the following. We take two windows of data, okay? So either xt or xt prime. And if these two windows of data are close in time, okay, so less than a certain distance in time, for example, they are less than 2 minutes away in a sleep recording, then we will say that it's the same label. So we'll say that the target is a +1. We need to predict +1. But now if you take two windows, one which is here and one which is basically at any place outside of the neighborhood of your basically anchor window, we will say it's a negative sample. So basically you take your raw data and you can generate this kind of almost infinite binary classification problem, so infinite sample size, where here you try to predict, giving two windows, can you predict if they are close in time or far in time? So it's a fairly simple idea. related to theoretical work by Yvarinen on permutation contrastive learning, and also other approaches which are a bit more involved, like which are called CPC for contrastive predictive coding, published now a couple of years ago. So we do this on sleep data, and we use the sleep staging, so basically predicting hypnogram, as the interesting downstream task, really the task that we want to solve. So we use this data, and the other data set that we use is another clinical context where people are recording using EEG, and you want to basically say if the brain is okay. So people imagine have a trauma, a brain trauma, and we put EEG, and we want to say, okay, is the EEG normal or is the brain injured? And you end up with this classification problem. Is it a normal EEG recording or abnormal, which is a binary classification? So what we see after doing these types of learning strategy is that we can learn with much less labeled data. So what you see on this graph, on the x-axis, is the number of labeled samples in the training sets. And what you see on the y-axis is the accuracy of the problem. So here it's balanced accuracy. And what you see is that even if you have roughly 10 samples among the 5 class, so you only have 50 samples, you're already able to predict well above chance. Basically, chance level is 1/5, so basically 20% accuracy. So here, with only 50 samples, you're already way beyond accuracy level. Sorry, well beyond chance level. And this is also replicated on this binary classification problem on clinical EEG. So really, this is really opening a new door by trying to learn with very few labeled observations in the biomedical context, which is for me an exciting route. Something that I was also particularly excited when we applied this on these types of data is that if we now take these representation that is roughly 100-dimensional, the outputting of the feature extractor, and we project this in 2D using a nonlinear transform here, which is based on UMAP, what we see is that the projection, the low-dimensional representation of the data is very well structured. You go from awake to very deep sleep before going back to REM sleep, and see the intriguing aspect was related to age. If we looked at how the subjects are spread over this 2D embedding, you see that the old people are basically projected here, and the young people are projected here. So what is a bit fascinating here is that you see that the network has learned that basically when you get old, your brain pattern is changing. This I will skip, and I will conclude in order to respect my delay. So hopefully I've convinced you that neuroscience has many interesting things to still yet to be done with. I'm heavily convinced that neuroscience signals are still underexploited in these days, and we still need to develop better tools to basically make sense from this complex data using interdisciplinary work between computer scientists, statisticians, neuroscientists, clinical or cognitive, and physicists that allow us to have for some of the audience who are frustrated because there's almost no math in my presentation, but I invite you to look at the papers if you want to have the math details. And for this, I would like to conclude by thanking all the people that have worked on this project. You see their names here, and I will stop here. Thank you very much. Could you hear me well during the whole presentation?
Yes.
I think
it was perfect.
Okay. Cool. Is there any question? Shall I look at the chat, or did anyone type any question?
No, but if anyone has a question, maybe they can turn their microphone on and speak. So let's maybe wait just for a couple of minutes.
Alex, can you hear me?
Yes.
So Philippe speaking. So I would like to ask you a question about the dictionary learning part,
Yes.
second part of your presentation. So how do you handle the delay ambiguity between your spikes and your waveform in your optimization procedure or in the prior you impose on your solution? Because any shift in time in your waveform can be compensated by a shift in the opposite direction on the spike.
Yeah, this is very true. Basically, if I rephrase and I illustrate, basically I can center my atom rather than starting here. I can center my atom here, and say that the spike is really at this instant. So the way we handle it is basically we have two strategies. So one which I omitted is basically that we say that first of all the atoms they start from zero and they go back to zero. So kind of the atoms are windowed. They have most of the energy at the middle of their in the middle. And this is something that we enforce during the optimization. We have these windowed atoms, and then we kind of cheat in the sense that we realign the atoms based on the maximum of the atoms that we found. So basically, we correct this indeterminate problem by shifting both the z, so the green activate z accordingly, in order to have the spikes at the maximum of the atom.
Okay, thanks.
But it's really a gory implementation detail.
Okay. Thanks a lot.
Any other question?
Bonjour, c'est Olivier. En fait, moi j'avais une question. Dans ton dessin où tu as les trois modalités là, tu as la matrice de rang 1 plus les instants.
Ouais.
La matrice de rang, j'ai l'impression que les atomes ils ont une certaine longueur. Comment vous les choisissez? Les
I don't
VL.
know if there's any non-French speakers. So I will answer in English. So
Okay.
the question is how do we choose the length of the atom? That's a very good question, and also that has some theoretical underpinnings. Even if the atom is really of length, let's say 50 milliseconds, what is the good strategy for the length of v? And what we partially understand and clearly observe empirically is that we should use a length of v which is bigger than the true support of the actual atoms to have a good recovery. And in practice, at least for this application, we know that we have this idea that we have atoms which are corresponding to, let's say, 50 or 100 or 20 or 200 milliseconds, and we enforce this. But a natural extension of this work would be to be able to have different resolution. That's been done in the past by other papers, other groups that have approached this with a multi-scale approach, where they first fit the atoms with the big receptive field, the big lengths, and then they try to fit smaller ones. It adds another parameter. So far, we haven't tried to do this, but it's yes, clearly there's a strong hypothesis about the size of the atoms that we are proposing to recover.
Okay.
Alexandre, this is Victor. Maybe I have one short question. I don't think I am not sure you've mentioned this, but in your optimization procedure, so when you optimize with respect to Z, U, V, of course the solution is not unique, right?
Yes. So the problem is not globally convex.
Yes.
Okay. So basically you're doomed to end up in a local minimum, which makes it tricky to make plots in terms of convergence rates, because you have different solvers that end up in those different local minima. But I mean, still you can manage, let's say. And basically with this, maybe one important question would be, okay, so you alternate between Z and this, but okay, do you alternate between Z, U, and V, or do you optimize jointly U and V by basically stacking the two vectors in one and doing an update on the extended vectors of the concatenation? This is things that we've explored in a quite empirical approach in practice. But
Okay.
if you look at the paper, we discussed a bit what are the strategies, and in the end we end up with this proximal, so this projected gradient descent, because we have these constraints that the vector should be less than 1 to fix this ambiguity of scale, because otherwise you could divide U by 10 and multiply V by 10. And so there's this recurrent issue when you use these types of dictionary learning strategies.
Yeah, of course. But then, so if there are local minima for U, V, I mean separately, maybe there is only one minimum for the product, UV transpose, or maybe Z convoluted with UV transpose?
So that's a good question. So I mean, you have this. So it's a bit like ICA. So as Philippe pointed out, you have clearly you can find equivalent solutions by shifting Z backward or forward in time and shifting V accordingly.
Yes.
And that would give you another completely equivalent solution. So you're in a setting where you're basically, if you're wondering what is the identifiability of this model, it will be identifiable up to these types of shifts,
Yes.
maybe also up to permutations, because there's no obvious order between the U, V, and Z. And so you might wonder, okay, what can I guarantee in terms of identifiability of this model? And so this is, I think, really a big part of the research project of Thomas Moreau to also look at these issues. But there has been some previous works, for example, the fact that the atom you should see the pattern enough, and then if the pattern should not overlap too much. And if you start to make these types of assumptions about the signals, basically you need to make assumptions about the data in order to guarantee it's related to, it's just like a hypothesis. The kind of the pattern should happen enough, and when it happens, it should not happen overlapping with each other. And so
I see. Okay. All right. Thank you very much.
Thank you.